this first equation of motion, I'm going to start with average acceleration, and I'm going to manipulate this particular formula so that I have my final velocity by itself. If y'all remember literal equations from like algebras, literal equations are all these variables, and we want to get one of them by itself. So to get my v of f by itself, I'm going to multiply both sides by this change in time, right? And if I multiply both sides by change in time, I'm going to get my average velocity times this change in time. And that equals my final velocity minus my initial. My final velocity is still not by itself. What do I need to get final velocity by itself? What do I need to do here? I need to add my initial over. Yes. And so when you solve for v of f, what you have is your final velocity equals your initial velocity plus your average acceleration times your time. Your average acceleration times your time. They point out that it resembles your y equals mx plus b there because you have an initial and you have a slope times a time, right? It looks similar to a linear equation there. You can have then a time velocity graph. This has uniform acceleration. My acceleration is not changing here, as you can see from the slope. What does this tell me? Oh, this tells me that I didn't start at zero velocity, right? Does everybody see that? So your y-intercept, so to speak, tells you your initial, your starting point. And then this tells you your change. How is it changing? The change in velocity then is going to be your acceleration, right? Your acceleration is your change in velocity over your time, right? And so that's your y2 minus y1 over x2 minus x1. It's your slope. That's your slope of that equation. So let's look at the example that's there. It says the missile launched with an initial speed of 246 meters per second. The average acceleration of the missile during the 15 seconds of the flight was 175 meters per second squared. Draw a velocity time graph. Velocity time graph. Well, to draw a graph, we need some starting points and ending points. The starting points are pretty straightforward. Starting time, nothing. Starting velocity, they handed that to me, right? Starting time was nothing. Starting velocity, they handed to me. I need a second point. All right, I know the time of my second point, correct? All right, what did they give me here? 175 meters per second squared. That unit should tell you what they gave you because that is the standard unit for something that we've talked about. What is meters per second squared, the standard unit for? Acceleration. They just gave you your average acceleration. What we don't have is your final velocity, but we just did an equation for final velocity. Remember the equation for final velocity? Looked like this. I have my initial velocity plus my average acceleration times my change in time. In order to draw a graph here, I need my final velocity, my second set of points. And so I'm going to plug all of this in. My initial velocity, 246. I got that from my problem here. Plus my average acceleration, they gave me that too, 175. Times my time, 15.0. When you plug all of that into your calculator, you should get 2,871. Look at my problem. Look at my initial problem up here. How many significant digits do I have? Actually, all three of the measurements they gave me. 3. How many did I have in my answer? 4. I only need 3. So I am going to look at 1, 2, 3. This is my significant digit place. So I'm going to round it this place right here. 2870 is what I'm going to use there. And now I have my second pair. 15 seconds, 2,870 meters per second squared is my meters per second is my second velocity. So now I can graph. Now I can legitimately graph this because I have 2 points. All right. And so if you were to graph it, they did this in thousands. All right. So when you see over here, When you see times 10 to the third, that just means in thousands, right? So 0.246, they graph that around right here. This is my initial time, 0, and my initial velocity, 246. My ending time, 15. My ending velocity, 2,870. You do not have to, you could have written 1,000, 1,500, 2,000, 2,500. It would have been the same thing if you had made your units that way. They just wrote it in terms of thousands, all right? But that would be the graph of that. Okay, so we all know this guy. This is average velocity, all right? This is my displacement divided by my time. Displacement divided by my time. Let's say we get displacement by itself. How would we do that? How would we get displacement by itself? We need to multiply both sides by change in time. Change in time. So that's what it looks like when we get my displacement by itself. We have my average velocity multiplied by my time. Well, what is average velocity? Average. If I have two velocities, to find the average of something that I have two of, what would I do? To find the average velocity, I have two velocities. What if I wanted just my average and I didn't have time or anything? If you have two grades and you want your average of the two grades, what are you going to do? Add them and divide by 2. And so if you have two velocities and you're just finding average velocity, you're going to add up your initial and your ending and divide by 2. All right. So then what we can do is we can go back to our change in right here, back to this one, our displacement, and we can replace this with this. Just substitute. So we're going to take average velocity and we're going to plug in what average velocity looks like. And so that's what it looks like there when we do that. So when we are doing all of this manipulation, we're using what we know, and we're just either using literal equation, moving stuff around, or substitution. And so in this case, we said, well, to find the average of any two velocities, we would just add up the velocities and divide by 2. And you come up with this. Displacement is going to be 1/2 the sum of your final and your initial velocities multiplied by your time. Multiplied by your time. All right, if I want to find the displacement. So this graph doesn't tell me anything about the distance or the displacement, right? This graph strictly tells me time versus velocity, correct? And so now I want to figure out the displacement of this particular missile. I want to figure out how far it traveled. Clearly it traveled upward, but all right, so I'm going to say 1/2. What was my final velocity? What was my final velocity here? 2,870. My initial velocity here was 246. Over what period of time did that happen? 15 seconds, all right? So if you do all of this in your calculators, you should get 23,370. What unit? How far? How far am I traveling? I'm traveling in meters per second, so that's meters, right? Probably wouldn't leave it like this. It would be like if I had given you that many feet. What would you probably use if you were using that many feet? Probably miles, right? So in the world of meters, we would probably use kilometers here. Kilometers. How many meters are in 1 kilometer? Kilo? 1,000. If you divide that by 1,000, you're going to get 23.370. However, how many significant digits did I have? Remember? How many significant digits did I have? This was actually 0.0. So how many significant digits did I have? 3. All right. 1, 2. This would be my third significant digit. I need to round him. So it's going to be 23.4 kilometers is how far it traveled, the displacement. Positive 23.4 kilometers upward, or you could leave it as positive. So we're still talking about our first equation. Determining the displacement graphically then is what's called the area under the curve. the area under the curve. So when I show you the graph and what you saw before, the curve was actually a line, but it's going to be called a curve. You can think of the curve as a generic and a line as a more specific, okay? And so determining displacement from velocity is the area under the curve, whereas determining velocity from position or displacement is actually the slope of the tangent. Remember we talked about slope of the tangent line? So slope of the tangent line refers going from like position to velocity or velocity to acceleration. When you go backwards, when you go from acceleration to velocity or velocity to position, you're looking at area under whatever was created from that graph, all right? Whatever was created from that graph. And so we're going to use our graph that we did before without numbers. We're just going to look at kind of the way it's set up, which is what's in notes there. So remember we had initial velocity that was not zero, right? Initial velocity was not zero. It started above the graph on the left-hand side. It went to an ending velocity here, an ending velocity right here, okay? So if I wanted to find the area of that whole entire thing, I would need the area of this triangle, right? Plus the area of this rectangle. Does that make sense? If I wanted to find the area under the whole thing, all right? Area of a triangle. Area of a triangle is 1/2 base times height. All right? Everybody agree with that? 1/2 base times height. So area of a rectangle is just the base times the height. So if we look at this rectangle piece right here, this base is my change in time. Yes? Everybody agree with that? This height is actually my initial velocity. So the area of this rectangle is my initial velocity times my change in time. So far, so good. All right, let's look at the triangle. Triangle is 1/2 base times height. 1/2, that's easy. My height here is still my change in time, or my base is still my change in time, rather, 1/2 my base. My height, however, is my velocities. My final velocity minus my initial velocity, that's my height. So 1/2 your base times your height. That's the area of the triangle. Yes? All right, so if I were to distribute, let's see. So I'm going to distribute this right here. I'm going to say V sub I times T, I'm going to leave alone, plus 1/2 at final velocity minus 1/2 initial velocity, right? And then that is being multiplied by my T, change in time. All right. I'm going to do a little bit of manipulation here. I'm going to factor out this change of time. Okay, factor it out. Change of time is factored out. I'm left with initial velocity plus this group here. 1/2 my final velocity minus 1/2 my initial velocity. I can combine these two, 1 and negative 1/2. What is 1 and negative 1/2? Give me. 1 plus negative 1/2. Just 1/2. So I have 1/2 my final velocity plus 1/2 my initial velocity. Change my change in time. There we go. And I'm going to factor out my 1/2 now. 1/2 my final velocity plus my initial velocity, and that is all being multiplied by my time. That looks very much like the same graph, right? Looks like the same exact equation. So both the algebraic and the graphical gives you the same answer when you're trying to find displacement. Whether you do it algebraically from the known equations or whether you do it graphically from your geometric equations, area of a rectangle, area of a triangle, you're going to get the same one. And the same one is going to give you how to solve for position. If I need to know my position, I'm going to say 1/2 the final velocity plus the initial times my change in time. That's going to be what I'm going to get every time. The second equation of motion is useful for finding your position, but not just your displacement. I'm not talking about your displacement. I'm talking about your initial or your ending position, your final position or your initial position. All right. And so we found average position, that's called displacement. And now we're going to look at how do we manipulate it to get my, maybe my final position or my initial position. In this case, we're going to stop at final. All right, so we're going to start with how do we get this? How do we get this particular equation here? Well, if I wanted to find my change in position, I can take my final position and I can subtract my initial position, right? Well, if I wanted to get final by itself, I'm just going to add this guy over. And so my final position is the same thing as taking my initial and adding to it how it changed. Doesn't that make sense? My initial velocity, my initial position plus how my position changed should be my final position. That makes sense, right? And so we start with this guy. And what we're going to do is we're going to go through and we are going to use what we used before to kind of manipulate a new equation. All right, so we are going to actually go back to my average velocity and my average acceleration. Let's see what order they gave me these in. Okay, well, we're not going to start there. So hopefully we know this particular equation right here. This is my average acceleration, right? Average acceleration. I take my velocity final minus my initial over how much time it took me to do that, right? On your quiz, you had going from 60 to 80 miles an hour, whatever, subtract, divide by the total number of seconds it took you to do that, right? And so that's what we're finding when we're finding average acceleration. So we're going to start there. All right. What we're going to try to do is we're going to try to get this little group by itself. So if I want to get that by itself, I'm just going to multiply both sides by change in time. All right. So far, so good. Now, here's the thing. We're going to go back to our equation that we had when we were working through it, manipulating these particular functions. This is what they get. They get my, another way to write displacement is going to be initial velocity times time, 1/2 acceleration times the time squared. And so that's one of them right there. Now, here's the thing. I want to find my final velocity. I want to find my final velocity, my final position. So I'm going to do some more manipulation. I'm going to use this guy right here, and I'm going to replace some things. So I'm going to replace this, and I'm going to keep this, and I'm going to replace this. I'm going to take this whole thing right here, and I'm going to replace it there. So we got this from how we solved for it. We're going to replace all of it. I'm going to say, well, to find my final position, I need my initial position. I need my initial velocity and my time, my acceleration and my time. This equation comes from these two. It comes from this one. That's just my average position. And it comes from manipulating all of these to replace this guy. All right, so we have my final. This should be on your worksheet, your handout. My final is my initial plus my velocity times time, 1/2 acceleration times squared. 1/2 acceleration times squared. 2 is we are going to take our average velocity times our change in time. All right, we get that from average acceleration. All right, average acceleration. So what you'll notice is this and this are the same, correct? So we're going to do substitution. We're going to take this and we're going to plug it in there. So I have my change in x equals my initial velocity times my time plus 1/2. And I'm replacing that with my average acceleration times time times change in time. All right. Nope, we're going to get to it. I just want to show you where it comes from. All right. So I have change in time times change in time. How do you think I can write that? If I had like a times a, how would you write that? A squared. So that's how I'm going to write it. I'm going to say 1/2 average acceleration times change in time squared. All right. this is another way you can write that position. And so, all right, so there will be times when it creates a quadratic. Not always, but sometimes. The second equation, your independent variable is your change in time. Your dependent, what you're solving for, is your final position. You have some constants in there. So your acceleration, your average acceleration is going to be a constant. Your initial position is going to be a constant, and your initial velocity is going to be a constant in that equation. All right? And so when we set these up, that's kind of what can happen there. It's a quadratic because if you think about it, position can be two places. Like if I were to throw a ball up, there could be two places that it would be at the same position, on its way up and on its way down. And so sometimes it's a quadratic because there's potentially two different areas. Not always, but sometimes. All right, position over time. Position over time then, and you don't have a graph yet, but we're going to go through some. You have to think about that my time is changing while my position is changing. Even though this is sloped, remember my acceleration is going to be the slope of the tangent line at any one point of the tangent line, because I have to go from position to velocity to acceleration. And so you can graph the time to position or you can graph the time to acceleration. It just depends on what they want you to graph. All right, let's look at what happens then when we don't know the time. This is useful when the time interval, this is your blank on your little handout, time interval is not known. So my third one, so my first one was when my displacement was not known. My second one was when an actual position, like a final position, is not known. And my third one is when my time is not known, when my time is not known. So let's walk through how we get this. How do we get the first time? We're going to go back to our acceleration. Our acceleration looks like this. All right? What would I do to get time by itself? Change in time by itself? Yeah, you can multiply both sides by that change in time. And then we need to divide both sides by what? By the acceleration, right? You don't have to write this part down, but you do probably want this one. Acceleration yields this one. This is the one that's the first one on there. Change in time, then. Change in time is the same thing as your final velocity minus your initial velocity divided by your acceleration, your average acceleration. And so that's one thing you can do to find time. If you have your velocities, your two velocities and your acceleration, you can find time that way. All right. And then we're going to look at one of our change in x's. So one of our displacement ones looked like this. This was one of them. So that next little block, go ahead and write him down. This was one of them from the very beginning. Remember, our first rule, our first equation was if you need your displacement, you can say 1/2 your final velocity plus your initial times your time. Okay? However, we no longer know time. This one's going to help us find our time, right? And so one of the things that we can do is we can take this right here, assuming we don't know time, and we can replace time with it, right? We just said change in time is my final minus my initial velocity over acceleration. So let's replace that time with this. Replace that time with this, all right? Looks like that. I just put it over 2, by the way. So this whole group over 2 times what I replaced this with, all right? So I took this equation, I replaced my change in time with it. I just substituted. Now this looks hideous, by the way. This does not look good at all. So we're going to make this look a little bit more simple. Side note, hopefully you remember this. What happens when I multiply something like this? What happens when I multiply something like that? I FOIL it. What happens? It's a special case. It's a squared minus b squared. My middle term cancels out. It's a special case, right? Multiplying conjugates. What do you notice about the numerators here? What do you notice about the numerators here? They're conjugates of each other, right? So what do you think would happen if I multiplied those two fractions? I would get the first one squared minus the second one squared, right? And on the bottom, I would just have 2 times my acceleration. Everybody see that? Yes? No? I promise that's what happens, but you can foil it. We'll look at it. You're just multiplying your numerators and your denominators. So if I take this, if I were to multiply v of f times v of f, I get v of f squared, right? If I multiply v of f times negative v of I get a positive v of f, v of I. Plus, if I multiply these two, I get a positive v of f, v of I, right? And if I multiply the last one, I get vi squared. What happens to my middle terms there? They cancel. So I end up with my initial velocity, my final velocity squared minus my initial velocity squared over 2 times my acceleration. And that's how you can find displacement, and you don't even have time in there. There is no time in that equation. So this is trying to find your displacement when your time is unknown. All right. Remember that long one we just did? We just did the long one. X final was my initial plus. I had basically my change in x, right? It's my initial plus my change in x, right? To find your final, where you started plus your change in position, right? Well, now I've just redefined my change in position, correct? So there's yet one more way you can find your final position. This time, what if you don't have time? You can just replace him, and that's where we get this equation from. Let's say I don't have time, right? I can't use my original one that I just had. I can now replace this with this one that I just found, the change in position when I don't have time involved, So the summary, we have 3 equations of motion. The first one is to help you find your final position. So you need your initial position, you need your acceleration, you need your change in time. All right, so this is what we ended with when we went through all the different steps to derive this particular equation. This is what you need for your final. The second equation is when you're trying to find displacement or position, and there are 2 options there for that one. And then the third equation is when you don't know your time, okay? So when you don't know your time. So it just depends on what you're trying to find in all of this. If you're trying to find velocity, if you're trying to find position or displacement, or if you're trying to find position or displacement without time. Those are the 3 things that these equations will help you with. All right, so this example says a train is traveling at 26.8 meters per second, slows at a constant acceleration of 0.500 meters per second squared. How far does the train travel until it comes to a stop? How far does it travel until it comes to a stop? All right, so let's talk about what we know. Traveling at a rate of 26.8 meters per second. What is that? What is that telling us? This is the starting velocity. It is telling you how fast it is traveling, right? Starting velocity. It slows at a constant acceleration. That's pretty obvious what it's telling us there. Acceleration of 0.500 meters per second squared. By the way, anytime you see meters per second squared, that's going to be a clue that it's acceleration. Meters per second is going to be a clue that it's velocity. So yes, it is very important that you notice it said slow when we start to put those down. All right, how far does it travel until it comes to a stop? That word stop is actually telling us something. What is that telling us? So we have initial velocity. That is going to be 26.8 meters per second. We have final velocity. That is 0.0 meters per second. And by the way, when you're thinking significant digits, 0 is not technically a measurement, so you don't have to count that as part of your measured significant digits. So when you see zeros, you're not going to be like, oh, well, they only wrote 0.0, that's only 2. There are no significant digits actually in that 0.0. All right, so you don't count that for significant digits. We also know our acceleration. All right, our average acceleration here is what they're giving us. And yes, it is a negative because they said that it slowed at a constant acceleration of negative. So we're going to say negative 0.500 meters per second squared. What you'll notice is that we do not know time here. We are going to use the third equation because we really don't know anything else about it to plug in, but we have the final velocity, we have the initial velocity, we have the average acceleration, don't we? And so now we're just going to plug those in, all right? The final matters. I know it's 0, but the final matters because you're subtracting, okay? If my initial velocity was 0 and I was subtracting a 0, that really wouldn't matter. But because I'm subtracting from 0, it actually matters here. So when I plug this in, I'm going to say 0. Of course, the square doesn't really matter, but technically it's squared. Minus my 26.8 squared over 2 times my negative 0.500. All right? So when we do that in your calculators. You're going to get a rather large number, not too bad. We should have gotten 718.24 meters. Yes, hopefully meters. So let's look at our, this is actually meters per second. So when we square it, you get meters squared and seconds squared. Down here, you get meters per second squared. I'm just showing you why you can check your units. The second squares will cancel. One of the meters will cancel, and you're going to be left with meters, by the way. So that's why that works. Now let's talk about significant digits here. Significant digits of the measured. Remember, 0 is not considered a measured. How many significant digits do we have here? 3. How many do we have here? 3. What should my answer be? 3. So when I have something like this, I count from left back. All right. So I'm going to say 718. I'm going to round this to 3 significant digits. So this is going to be 718 meters because 3 significant digits is what you need. It's saying how far, right? So a distance per a time is going to be movement. So velocity is going to be meters per second, or speed, depending on which one you're talking about. Acceleration, meters per second squared. But if I gave you just a straight up distance, I would say I walked 3 meters to get to you. And so there is no per time if you're not talking about the rate of movement. You're just talking about the displacement, how far it went. All right, so if you had wanted to use the second one, you would have to calculate time first. So if you wanted to figure out your change in time, you're going to say, well, my final velocity minus my initial velocity divided by my constant acceleration, all right, is going to equal my time. So you should get 53.6 seconds there, all right? Now, if I were doing this, I would go straight to the equation with what I had, right? And I wouldn't try to calculate time and then go to the second equation and plug in time with all of those other things. I would go straight to this one because this one's easier with the information I've been given. But you could. If they said how long did it take, you could then answer that question as well. Here. Free fall, uniformly accelerated motion. This is based off of gravity. We are using the gravitational pull based on meters per second squared. If I said meters per second squared, what is that representing? Those units tell you it is what? Acceleration. So 9.81 meters per second squared. You'll often see it 9.8. And if you're just trying to estimate in your head, you can estimate at 10 and you'll be pretty close. If you're just trying to, hey, does this make sense? Answer. you could estimate it at 10 meters per second squared. You'll notice it says downward. So in an algebraic sense, when I say downward, I'm going to use negative 9.81 meters per second squared. All right, this is specifically on the Earth, okay? This is specifically on the Earth. Gravitational pull on the Earth, okay? If we were somewhere else, that is a different gravitational pull depending on the mass of what you're on. We'll also point out that for all of these examples that we're going to do, wind resistance is not going to be something that we take into consideration. You do have what's called a terminal velocity. So terminal velocity is that if you were to have a falling object, you have naturally wind resistance that pushes against it, right? So if something is falling, it doesn't just keep accelerating and keep accelerating. It is going to reach an equilibrium point with what's pushing up against it. And that's as fast as it's going to be able to fall. That's called a terminal velocity, all right? It doesn't mean it's the velocity at which you stop. It means it's the velocity at which you stop increasing accelerating, okay? And so if you were to drop something off of a really tall building, it would get to its terminal velocity and it would maintain that velocity. And you can see it. They've done experiments with like light blinking to catch it, and you'll see the acceleration go fast, 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 and then you'll see it space out and become constant, right? Because it reaches a terminal velocity based on wind resistance. But what we're doing with the questions that we have here, we're going to kind of exclude wind resistance and assume that there is no wind resistance on the object as it's falling. All right, even though, and different objects will have different terminal velocities. It depends on the shape, the size, the mass, etc. of the object. So now we're going to take those three equations that we had, and instead of acceleration, our acceleration is going to be the same thing. Our acceleration is going to be gravity. And so if we look at that first equation, final velocity, we're going to say initial velocity plus gravity times time, because gravity is our acceleration here, right? So we have an initial velocity. Let's say we chunk that ball off the bridge, right? But the acceleration of that ball, because it is not powered by anything else except gravity, is going to be gravity. If we look at our second equation, now this has a change in y, and I'm going to tell you why it has a change in y. You are welcome to leave it as x, because I feel like we've been using x over and over for it. The reason is because when we're talking about gravity, it's constantly moving up or down on the y-axis, right? Whereas other motion, like a train moving, can be moving this direction, right? We don't really have an axis, so to speak, but gravity does have an axis. Gravity is pulling down, if you were thinking about that. But you're welcome to leave it as change in x, and in my brain, I left it as change in x because that's what all the other ones were. Our third equation, again, this is going to be your change in x that we're talking about here. And we just replace 2a at the bottom with 2g, gravitational pull. And so these are identical to the ones we just did with acceleration, except now our acceleration is straight gravity because these are free falling. This is only for objects that do not have any other source of power. So like a rocket ship, right, when it is going off the planet, our acceleration is different than when something is falling. Falling is always a gravitational acceleration. A stone falls from a bridge high above a river, ignoring air resistance. What is the stone's velocity after 4 seconds? Velocity after 4 seconds. So we need final velocity. So we're searching for that. We are looking for final velocity. We need to plug in what we know. Initial velocity. A stone falls. What is its initial velocity? 0. Nobody threw it, correct? So 0. And then we are going to add to it. What does G stand for? Negative 9.81 meters per second squared. And we are going to multiply that by 4 seconds. Question. So in this problem, again, I'm gonna hone in on how we do these units, because units are something that people struggle with. Seconds are in the bottom here squared, and they're in the numerator on that 4 seconds. So those will cancel, and I'll get meters per second. What is meters per second? Velocity, which is what they asked me about, correct? They asked me, what is the stone's velocity? So I'm just going to multiply. When I multiply, what do I get? I get negative 39.24. All right, let's look at our original problem. What did they measure? 2 significant digits is what they measured. 2 significant digits is what they measured. I need 2 significant digits here. So how am I going to do this? Negative 39 meters per second is my velocity after 4 seconds. Something is falling, your velocity is going to be negative, right? Does that make sense? The other thing is a quick and easy rounding of gravity is a 10, negative 10. So negative 10 for 4 seconds is approximately negative 40. Does negative 39 make sense? Yes, it does. So do you see how I did that as a quick, does my answer make sense? 10 is a rounding of gravity. Negative 10 is rounding. We're not going to round that much. But if you did, you could do a quick check. I fell at negative 10 meters per second squared for 4 seconds, approximately negative 40 meters per second. Right? And so a negative 10 is an approximation of gravity, and you can see if your answer makes sense. Negative 10 for 4 seconds, negative 40 makes sense. Negative 39 then makes sense when I did it exactly. All right? So A was asking for final velocity. How far, what does that want me to tell them? Distance, displacement, yes. So I'm going to use my displacement. One of my displacements. So change in X. That's what we're trying to do here. We're going to say initial velocity, it fell 0 times how long it fell, 4 seconds, right? We're going to add to that. And yes, in your calculator, you can just put 0.5. That's 1/2. Gravity, that's negative 9.81 meters per second squared. Times our time squared, 4 seconds squared. Okay, 4 seconds squared. So units, good question on units. I have seconds squared here, and it's going to count out with seconds squared there. So I'm going to end up with meters, which is how far. Right? When you do this, you should get approximately negative 78.48 meters. All right. Now here's the thing. It depends on what they're saying, but if they said how far, I'm thinking distance, which is the absolute value of your displacement. Okay. And so you likely would not include a negative here because it's saying how far. How far typically is asking distance. It did not say anything about the direction. All right, it told you it was falling, so we already knew that. So if you did this, you could say it fell 78.48. We're going to get that to 2 significant digits in just a second, right? So that's kind of what you're going to think. If they said how far did it fall, then you're going to just list it as a positive because the falling piece indicates that it was a negative movement. All right, 2 significant digits then. 2 significant digits. So I need this digit and that digit. I'm going to say it fell 78 meters. It fell 78 meters. So a baseball player throws a ball straight up with an initial velocity of 22.8 meters per second. What is the maximum height that the ball will attain above the launch point? The maximum height that the ball will attain above the launch point. I know my initial velocity. In order for a ball to go up and come back down, this looks a lot like a parabola. We have a vertex. At the vertex of this parabola, it has 0 velocity. That is the turning point. That is the turning point, all right? And so the maximum height will always be at the turning point if you're throwing something up, all right? So we're going to say, well, how far? That answers the question, how far? We have a final velocity at the turning point, which is what we're talking about. We have a velocity of 0. We have an initial velocity. They have given us 22.8 meters per second as my initial velocity. I'm going to square that. On the bottom, I have 2 times gravity. Gravity is always negative here. 9.81 meters per second squared. all right? Meters per second squared. So you should get, when you plug this all in, what do you get? All right, so you should get 26.495, keeps going. How many significant digits did we have initially? Three. So we need 3 significant digits, which is 1, 2. That means we round this guy. So it should be 26.5 meters upward is what you can say if you want to, right? But it went up 26.5 meters. All right, let's talk about when does the ball reach a height of 19.5 meters above the launch point. So when does it reach a height of 19.5? 19.5 meters. What is that going to be? That's going to be a position, right? A position. So when does it reach that position? This is going to be a final position. All right. So if I look at my equation for this, we know our final position. All right. We know our final position, and I wrote it as V, but it's actually X of F. Sorry about that. We know our final position. All right. This says above the launch point. So if they want to know above the launch point, then our initial position is 0. He's initially 0 above the launch point, right? 0. We know our initial velocity. They actually gave us that. They gave us initial velocity of 22.8, correct? We do not know our time. Our time is actually what we are going to be solving for. All right. And then we have 0.5 times gravity, right? Now we know gravity is my acceleration. And then we have time squared. All right, so let's simplify this a little bit. So I'm going to go ahead and multiply this out. All right, I'm going to go ahead and multiply this piece out. What is 0.5 times my negative 9.81? All the way out, because we're just negative 4.905, and then we have time squared. To that, we are adding 22.8 times time. And then I'm going to move this negative 19, I'm going to move that over and set everything equal to 0. Now, if I were to rewrite this, and instead of time, we're going to say, for change in time, we're going to write that as x, just because my brain needs to see it that way. Then I have negative 4.905 x squared plus 22.8x minus 19.5. What type of equation do I have? I have a quadratic with a negative a. Tells me it's points down, does it not? So if I have a parabola pointed down, doesn't that look like what a ball is going to make if it's thrown up? Yes, it does. Yes, it does. How do I solve a quadratic? I'm definitely not going to factor this thing. Am I? No. No, I am not going to factor this. I am going to use a formula that we should know. So in your calculator, you really can do, in your calculator, you can do parentheses, negative b, just do plus, because you want your calculator to actually calculate it. Plus the square root. This should open up a parentheses in your square root. If it doesn't, then put a parentheses. B squared, you should be able to do 22.8 and do your squared button, right? You should be able to do that. Minus, it's going to do order of operations, 4 times, I'm just putting a parentheses there because it's negative, times C, all right? You're going to have to close the parentheses inside your radical and outside your radical because that's your numerator. Divide by, open parentheses, 2 times negative 4.905, close parentheses. You get 2 answers. You get 3.52 seconds and you get 1.13 seconds that it is at the height 19.5. Why would you have 2 times that it is at the height 19.5. Prior question was 26.5. On the way up, it hit 19.5. It went all the way to 26.5, whatever. It came back down and hit it again. It is logical that you have two answers here. It is logical that you have two answers here. There is homework. So I have these two problems for homework. I want you to try them. Don't panic over them, but I want you to try them. On Thursday, we will go over the homework.